Good day, viewers all over the world. You are welcome to Toydale online class. So today we want to talk about mathematical induction. Mathematical induction. So the principle of induction applies to the set of natural numbers because they are well ordered. You recall that when we discussed the set of numbers, I said there are 6 set of numbers that we discussed. We talked about the natural numbers, we talked about the integers, we talked about the rational numbers, we talked about the irrational numbers, we discussed about the real numbers, then the complex numbers, which happen to be the last numbers. But every other number apart from these natural numbers are said to be apart from all the it's only natural number that are said to be well ordered. Well ordered in the sense that it has a starting point. The first element under the natural number is 1, 2, then up to infinity. But in case of integers, it starts from minus infinity, so we don't really know the starting point. In the case of rational, irrational, real, and complex. So the set of natural numbers are said to be well ordered, and that's why we can talk about induction on the set of natural numbers. So if we want to discuss about mathematical induction, so we can actually take any number n from the set of natural numbers, and we can define a function on that number, or if you don't want to call it a function, we can say assertion on that number, or we talk about preposition of the element of that number. Then what do we do on mathematical induction? We are going to test for when n is equal to 1 and try to check if it will go. Then after n equal to 1, we go to n equal to k. Then we check if it is true. When n is equal to k, if it is true, then if this is true, then that implies that k plus 1 will also go on under the consideration. So that is what we do in mathematical induction. Is that we call it a function. We call it as assertion or preposition. We can actually define it with any of these. So any question we are given, we can refer to it as a function, assertion, or preposition. So we check for when n equal to 1. Then we now check for when for all k equal to for n equal to k. It must implies that k plus 1 is also true. That is what we check under mathematical induction. In other words, the principle of induction is stated as follows. That is, if a set x, if you have a set x, if a set x of natural numbers, if a set x of natural numbers is such that Roman figure I 1 belongs to x, that's the first one. Then Roman figure 2, for all k belongs to s, implies that k plus 1 belongs to x. Then we say that s is equal to a natural number, and that's what we check. So every problem under mathematical induction, this is what we do. This is the summary of everything. That if you have a set x, we denote a set by capital letter, an element of the set by small letters. So if you have a set x of a natural number, so this set s automatically must be a natural number. That is, must be positive counting all numbers, excluding 0. So if you have a set x of natural number such that 1 belongs to that set, then for all k that belongs to that set, implies that k plus 1 also belongs to that set. If you're able to establish this, then we say that x is a natural number. Then we can actually talk about mathematical induction. So I'm going to give example. We are going to consider about 3 or 4 examples here. So let me start with the first one. Example 1. Proof by mathematical induction. Let me just call this the abbreviation. MI, mathematical induction. Proved by mathematical induction that 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equal to n squared. So this is what we want to show. We want to prove by mathematical induction that the summation of all this can actually give us n squared. Then what are we are going to check for this n, since we have n here. We check for, either we call it function. I said if we can call it, we can say f of n, that is, we are referring to this as a function, or we can do say a of n, we refer to it as assertion, or we say p of n, that is as per precision. So I'm comfortable with this f of n. I'm comfortable with function of n. So we now say the first one, say f of n is such that 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equal to n squared. So now let's start the test. The first one, we check for f of 1. Look at the left hand side here. What is the first value here? F of 1 here is what? The first value here is 1. And let's look at the right hand side. F of 1 is when n equal to 1. And what would that give us? F of 1 will be 1 squared, which is equal to 1. Then f of 1 is true. That is, the first value here is 1. Then if we go to the right hand side, substitute when n equal to 1, what do we get? We are able to get 1. That shows that f of 1 is true. Then we move to the second one. So we move to the second one, which is f of k. So let's assume we are not sure. We say let f of k be true. That is, we are not sure, but we want to assume that f of k will be true. That is, what do we get under f of k? F of k, we now say f of k such that 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. Wherever you see n here, you change it to k. Will be equal to what? K squared. When it is 1, we substitute n to be 1. Now, when it is f of k, of course, k is a constant, positive constant. So instead of n, we are going to change it to, we change n to k. So this is what we have here. Then we let f of k be true. We are not sure. But if it implies that f of k plus 1 is true, then we'll be able to verify. Then the last one, we want to check for f of k plus 1. In this case now, f of k plus 1 will now be, we first write for f of k, 1 plus 3 plus 5 plus dot 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 plus 2k minus 1, then plus, in this case now, we now have 2. Instead of k here, it is k plus 1 that we have 2 into bracket k plus 1 minus 1 will be equal to what? K plus 1 all squared. That's what we get at the right hand side. That will be k plus 1 all squared. So what do we do here? We now say, you know that when we check for f of k, here f of k, all what we have at the right hand side here, and at the left hand side is equal to k squared. So this is what I will do. For k plus 1 now, I will now change everything here. Everything that I have here, I will change it to k squared. It's the same thing, because the left hand side is assumed to be equal to the right hand side. So instead of 1 plus 3 plus 5, everything up to this place, I'll change everything to k squared. So I'm going to have k squared plus, I will now expand this. I will have 2k plus 2 minus 1. Then I'm going to have k squared plus 2k plus 1. So let me express this. Of course, this is a quadratic expression. I should be able to factorize this. So I'm going to have k squared plus k plus 1. So when I do the grouping, I'm going to have k is common, k plus 1. Then plus 1 is also common, k plus 1. At the end of the day, I will combine this. So I'm going to have k plus 1 into bracket k plus 1. Then this is k plus 1 squared, which is equal to what we have at the right hand side, k plus 1 all squared. So we have been able to show that if we assume that f of k is true, then we have that must implies that f of k plus 1 must be true. So we have been able to show that k plus 1, the value we got at the left hand side, is the same thing as what we are going to get at the right hand side. So we now say, therefore, f of k plus 1 is also true. And we will now say f of n is true for all n that belongs to a natural number. So we have been able to show what we have been able to prove by mathematical induction that what we are given at the left hand side is equal to what we have at the right hand side. And that is what we do under mathematical induction. So I'm going to give another example. So that will serve as second example. So I'll give another example, which will be second example. So example 2. We say the question says that. So example 2. Okay. Proof by mathematical induction that 1 times 2 dots connote multiplication in mathematics, plus 2.3 plus 3.4 plus dot 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 plus n into bracket n plus 1 is equal to n all over 3, n plus 1, n plus 2. So this is what we want to show by mathematical induction, that the left hand side, that's what we have on the board, is true. So that's what we are given. That's what we want to show. So what do we do here? Of course, we start with n equal to 1. So we say f of n is defined as, this is what is defined as 1.2. That's 1 times 2 plus 2 times 3 plus 3 times 4 plus dot 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 plus n multiplied by n minus plus 1. So that's what we are given. Is equal to n all over 3, n plus 1, n plus 2. So we now check the first one. We check for f of n, f of 1, when n is equal to 1. F of 1 is the first value here at the left hand side. That's 1.2, and that is equal to 2. 1 times 1 is 1 times 2 is 2. And we substitute when n equal to 1 at the right hand side. We have 1 all over 3 into bracket 1 plus 1, that is 2. Bracket connote multiplication into bracket 1 plus 2, that is 3. That is 3. So 3 can cancel 3. 1 times 2 is 2. So both left and right hand side is true for f equal to f of 1. So we say, therefore, f of 1 is true. Why is it true? What you have when you substitute the first value when n equal to 1, that is, this is the first value when n equal to 1 at the left hand side is equal to 2. When you substitute for n at the right hand side is equal to 2. So that is true. Then we go to Roman figure 2. We now say, we assume, we are not sure, let f of k be true. That is, we want to assume that f of k. So in this case, now instead of n, we change everything to k. We have 1.2 plus 2.3 plus 3.4 plus dot 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 plus k. We change n to k into k plus 1 is equal to k all over 3 into bracket k plus 1, k plus 2. That's what you get. So we make that assumption for k. Since we are not sure, we now go to f of k plus 1. That's the third one I want to show. So we show for k plus for f of k plus 1 now. So what do we have here? We write everything 1.2 plus 2.3 plus 3.4 plus dot 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 plus k plus 1 now. Instead of k, wherever you see n, we change it to k plus 1 into bracket. Instead of n now, we change it to k plus 1. So I'm going to have k plus 2 to be equal to n will be k plus 1 all over 3. Instead of n here, n is k plus 1, that will be k plus 2. I'm going to have k plus 2. Then this one will be k plus 3. So we want to show that this is equal to this. So no. There's an omission. there's an omission here. We first write for k plus 1. K into bracket k plus 1 before we now move to k plus 1 and k plus 2 to be equal to k plus 1 over 3, k plus 2, k plus 3. That's what you get. So from there now, when we let f of k to be true, you realize that everything that we have at the left hand side is equal to what you have at the right hand side. So from here now, up to this point, I will change it to what I have at the right hand side. Please, let's look at it very well. For f of k, is the left hand side here is equal to the right hand side. So I want to change everything now. I will change everything to k into bracket k plus 1, k plus 2, all over 3. Now plus k plus 1, k plus 2. So that's what we have. So when we look at this now, k plus 1 and k plus 2 is common. So what do we have left? We have k all over 3 plus 1 left in that bracket. So from there, we have k plus 1, k plus 2 to be equal to the LCM is 3. 1 in 3 in 3, 1, 1. So that's k plus 3. Then I can rewrite this to say k plus 1, k plus 2, k plus 3. Everything divided by 3, which is same thing as k plus 1 over 3 into bracket k plus 2, k plus 3. And that is what we are asked to show. Therefore, we say f of k plus 1. So we say f of k plus 1, in this case now, is also true. Is true. And f of n, which is the question, is true for all n that belongs to a natural number. So the number under consideration must be a natural number, because natural number are said to be well ordered. So that's what we get. So I will take 2 more examples, then we call it a day. So let me give another example. Example 3. Example 3. We have proof by mathematical induction that 1 cube plus 2 cube plus 3 cube plus dot 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 plus n cube is equal to n plus n into bracket n plus 1 all over 2 all squared. So we want to show this, we want to prove this by mathematical induction. So if this is what we are given, of course I will say f of n is such that 1 cube plus 2 cube plus 3 cube plus dot 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 plus n cube is equal to n all over n plus 1 squared. So we check for f of 1. Under f of 1, what is the first number here? It is 1 cube. So we are going to have 1 cube. What is 1 cube? It is 1. And we substitute when n equal to 1 at the right hand side. I'm going to have 1 into bracket 1 plus 1 all over 2 all squared. So here 1 plus 1 is 2. This is 2. 2 cancel 2. I will have 1 square, and 1 square is 1. So we have been able to show that f of 1 is true. Then we go to the second one. That second one, we let f of k be true. That is, we just assume that f of k is true. But we're going to use f of k plus 1 to show that f of k is true. So we now say f of k will now be 1 cube plus 2 cube plus 3 cube plus dot 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 plus k cube to be equal to k into bracket k plus 1 all over 2 all squared. So we assume that that one is true. Then we now move to the third condition that must be satisfied. We move to the third condition that must be satisfied, and that is the third one. So we now say f of k plus 1. So f of k plus 1. So we say, you can just say for f of k plus 1 to be true, we have, that is f of k plus 1 will now be this f of k. You write it, we now add f of k plus 1 to it. That will be 1 cube plus 2 cube plus 3 cube plus dot 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 plus k cube, then plus k plus 1 cube will now be equal to k plus 1, k plus 2, because when n equal to n is now equal to k plus 1 here, all over 2, everything squared. So what do we do here? So from here now, when we check for f of k, from here to here, we change it to this. So from this point now up to k cube, I'm going to rewrite it as k into bracket k plus 1 all over 2 all squared. Now plus k plus 1 cube. We don't do anything about the right hand side. So if I expand this, I'm going to get k squared into bracket k plus 1 squared all over 4. That is when I take the square of everything. That's what I'm going to get. Then plus k plus 1 cube. So from there, I can bring out k plus 1 all squared. It is common. I have k squared all over 4 plus k plus 1 all over 1 as the leftover when I bring this out. So when I concentrate on this, this is 4. I'm going to have k squared plus 4 into bracket k plus 1. That's what I have here. Then if I expand this, I'm going to have k plus 1 all squared into bracket k squared plus 4k plus 4 all over 4. And of course, I can factorize this. I can factorize what I have here so that I'm going to get k plus 1 all squared into bracket. When I factorize this, I'm going to have k squared plus 2k plus 2k plus 4 all over 4. Then I can rewrite this as k plus 1 all squared. When I do the grouping of this, I'm going to have k plus 2 all squared also. Everything all over 4. Everything all over 4. Then, if that is the case, everything all over 4, I can rewrite this as k plus 1 into bracket k plus 2, then 2, everything squared. From here now, this is what we get. Because this is k plus 1 squared, k plus 1 squared, 4 is 2 squared. So if I remove that square, I will have k plus 1 into bracket k plus 2 all over 2, then everything squared, which is equal to the right hand side, which is equal to the right hand side. So it's equal to the right hand side. So what we have done now is equal to the right hand side. That is, let me just write it out neatly. We have been able to show that k plus 1, k plus 2, everything squared is equal to what we have at the right hand side, k plus 1, k plus 2, all over 2, everything squared. So since we have been able to show that, we can now say, therefore, f of k plus 1 is also true. And f of n, the question, is true for all n that belongs to n. So that is how to check or to prove under mathematical induction. So I would love to stop here because of our time. So we continue from there in our next class. Thank you, and God bless you all.